continue this fourth edition of our webinar series with Sudipta Sarkar's presentation on Amal Kumar Raychaudhuri. And Sudipta is well known to the IIT Gandhinagar community, so I would not introduce him, but for outside listeners, I will simply mention that he's a professor of physics, specializing in topics ranging from relativity to quantum physics, and in particular, black hole studies. And he's been with the Institute for quite some years and is also deeply interested in history of science at many levels, from antiquity all the way to modern developments in the history of science. So Sudipta, the floor is yours, and we will be happy to learn about this great Indian physicist whom I'm sure few physics students know anything about.
Okay, thanks, Michelle. So let me first share the screen. Yeah, you can see the presentation, right?
Yes, yes.
Okay, great. Okay, so let me start. Can I start, Michelle?
Please.
Okay. Thanks everybody for coming here. And first of all, let me thank Madam Gandhi for this wonderful seminar, wonderful talk on Salim Ali. And it's really not easy after that such a beautiful talk to have another talk. So I'll try my best. So the person whom I'm going to talk about is a very, very famous Indian physicist, particularly an expert of general relativity, whose contribution in the theory of general relativity, what we call the Einstein's theory of gravity, has been remarkable. I mean, it is one of the very few, foundational contribution in basic sciences from India after post-independence. I mean, interestingly, Amal Kumar Raychaudhuri is not very well known beyond the particular circle of physicists. There are many reasons for it. First of all, his work is highly technical, mathematical, and therefore it is not sometimes easy to, comprehend the scope and the importance of the work. And therefore, I will try my best to give you a perspective of the person, as well as why physicists all over the world are, we believe that this equation is a foundational result in modern physics, particularly physics after Second World War. So you can see the picture of Amal Kumar Raychaudhuri, and I'm going to talk about this man and the equation named after him, which is called the Raychaudhuri equation, and why this equation has changed our view about the cosmos, our universe, the black holes, and everything forever. So let's start the story. So this is the picture of Professor Raychaudhuri. He born in 1923 and he left us in 2005. Incidentally, I entered into the field of physics, started my PhD in 2004. I never met him. Of course, I knew about him during my MSc days. He was already a legend for us. But it's unfortunate that I could never able to personally meet him. But I'm fortunate enough to study his field of work and working on his equations. So it's a really privilege for me to talk about him. So Amal Kumar Raychaudhuri is an Indian gravitational physicist and is popularly known as, AKR. And in fact, in post-independence area, his work on what is called the nature of gravitational singularity, which I'll try to explain, is one of the truly foundational results. So he developed a mathematical equation in 1950s, and that mathematical equation was applied by great physicists, and it has changed our view for science forever and led to Nobel Prizes after Nobel Prizes. More than that, he is also an inspirational figure for generations of Indian physicists. In Presidency College, Kolkata, he was created an academic atmosphere which is remarkable, and it motivated gifted students to take up research career to work in the fundamental sciences. And in fact, many of his students are now leading scientists in their respective fields. And if you talk to them, you will understand the kind of influence Raychaudhuri had on them. His textbooks, his teaching style, his lectures are known to be legendary. So when you give the story of such kind of person, such a physicist or mathematician or chemist or somebody like a scientist, particularly who worked on very technical field, it is necessary to see the context of their work. To know the context of Raychaudhuri equation, we have to start a bit early, rather from 16th century. And the right starting point, probably to understand Raychaudhuri equation, would be the famous incident, which we will all know, which may or may not happen. In case, it's actually quite interesting if you do have happened, is the idea of Newton's apple. We all know that Newton possibly, and also during a time of a pandemic, got influenced by falling of an apple and came up with a possible famous law of gravity. What is this law of gravity? The law of gravity, which Newton says that every two particles in this universe attracts each other by a force. And this force is controlled by a mathematical equation, which is I have given. Okay, this equation is a standard equation, even in class 8. I don't know, maybe in nurseries also people study. What is interesting is that Newton gave a mathematical law to understand the nature of the gravity. And this is extremely important. Okay. Previous to Newton, there are great scientists all over the antiquity in all cultures. But getting a mathematical law and therefore making a prediction is actually quite rare. Newton's laws were mathematical laws. Based to that, we can make predictions about the nature, we can create technology, we can change our universe. And the Newton's law is very similar to the Coulomb's law in electrostatic. But note that there's a very interesting slight difference. Gravity is always attracting, unlike electrostatic, where there are positive charges and negative charges attract each other, but two positive charges or two negative charges repel each other. There is no repulsion in gravitational force, simply because there is no negative mass. Gravity is always attractive. And we should remember this sentence, and we will see the Raychaudhuri equation will give you a very beautiful interpretation of this Newtonian fact to the Einstein's gravity. Good. So Newtonian physics remains valid till 1905. Everybody agreed that Newton's law is the law of nature. Great technological achievements took place on the basis of Newton's law. Most of the modern technology we see are based on Newton's laws of motion. And of course, our understanding of the heavenly bodies like the moons, the planets, the star, mostly based on Newton's law of gravity. This was actually quite remarkable. Please understand, Newton's law gave us the handle to know the laws of heavenly bodies. This is the first time man can make prediction about the cosmos. So that gave a great confidence in man that they can know the nature and possibly without even a creator. But in 1905, there was another scientific revolution. There was a clerk working in a Swiss patent office, revolutionized everything we know about the laws of motion. And the name is very, very familiar to everybody. Albert Einstein in 1905 wrote famous papers, 5 papers. Every paper is in a revolutionary war. But particularly this particular paper, which I have shown here, which is called, German is written, I am not going to read the German for obvious reason, but in English it is called the Electrodynamics of Moving Bodies. And it is this paper where Einstein gave the theory of special relativity. And he has shown the Newton's laws of motion, which are valid for last 400 years, people thought they are the laws of nature, is only an approximation. And these laws needs to be corrected for bodies moving at the speed of light, near the speed of light. Okay. Relativity theory demanded that the speed of light in vacuum is an universal constant, independent of the state of the motion of the observer. This is completely new law because, if you look at a train, the speed of a train depends on who is measuring it. If you're on the train, with respect to you, train is not moving. If you're on the platform, with respect to you, train is moving. But for light, it does not matter what your motion is. Everybody will measure the speed of light in vacuum to be universal number. So this is a new mechanics. So Einstein modified the Newton's laws of motion. And the question is, what about the laws of gravity? So next 10 years, 1905 and 1915, Einstein devoted himself to find a theory of gravity consistent with the theory of special relativity. The Newton's theory of gravity has no mention of anything related to the speed of light. Not only that, It seems that the gravitational force travels instantaneously in Newton's law, which is inconsistent with the theory of relativity. In relativity, nothing can move faster than the speed of light. Therefore, what Einstein aimed is to correct the Newton's law of gravity on the basis of his relativity theory. Now, this is not an easy task. It took Einstein 10 years, and it took me a full class to explain how to obtain a relativistic theory of gravity. And a full course is about 40 lectures. So I'm not even going to attempt here how to do that. But it turns out this relativistic theory of gravity, which Einstein found in 1915, which is considered to be one of the greatest achievements of human thinking, is entirely different from any known laws of physics. And this law we call the theory of general relativity. Theory of general relativity is a very, very unique law in the physics, science of physics. And what it asserts is that the presence of mass and energy changes the space-time surrounding it. It's somehow you can think of that there is some condition which mass and energy creates in its surrounding space-time, which we will call the curved space-time. And the gravitation is nothing but the manifestation of the curvature of space-time. So people who are mathematicians, they have started the mathematics of curved space-time long before Einstein, but nobody thought that this mathematics will ever have a practical application in our natural world. What Einstein tells you that the physics of gravity is basically the mathematics of curved space-time. Not only that, Einstein also gave a beautiful equation, and that equation is called known as the Einstein's equation. I don't want to explain this equation. It is rather very, very mathematically complicated equation, but it basically relates the curvature of space-time with the energy and the mass of the matter. So this equality sign at once relate the knowledge of mathematics, which was known by Gauss, Riemann, and many more people, and the physics knowledge regarding matter at once. So this is a remarkable, beautiful equation, a very, very elegant approach. And it turns out this equation has been verified observationally many, many times, even recently by the LIGO observations of the gravitational waves. So as I told you, this is a complicated equation. What one would like to see is that one like to solve this equation and obtain the gravitational field due to the matter. So this equation is a mathematical equation. You input matter, I give you the gravitational field out of this equation. So for example, you may say that I have sun. Sun is a spherically symmetric, it looks like sphere. It's a spherical body. And I may ask, what is the gravitational field outside the sun? In Newton's law, it will be simply like 1 by r squared. But in Einstein theory, you have to solve this equation and obtain the space-time, curved space-time outside the sun. And that solution will give you the nature of gravity. So when Einstein first developed this Einstein's equation, it was said, and in fact, he commented in one of his original papers, that it will be very, very difficult to solve this mathematical equations. And there are mathematical reasons for it. But it turns out that one could be able to solve his equation, in fact, within 3 to 4 years after the publication of this equation. And this was done by a remarkable German physicist, a German astrophysicist called Schwarzschild. And he was actually in the battlefield of First World War, and he was working inside the tank while the fighting was going on. He's solving Einstein's equations and finding out the space-time around the spherical body like star. So he died in the First World War because not from the battle itself, but from the typhus, I think. But his mathematical solution remains immortal. And this mathematical solution we call the Schwarzschild's metric. What is Schwarzschild metric? It's simply, it replaces Newton's law for outside a sphere, spherical body, by the Einstein's picture of gravity. And this is something I have written. You don't need to know about what is this symbols mean, but it simply means instead of a 1 by r square force law, Schwarzschild gave us how to obtain the curved spacetime solution, which will give the respect of gravitational field. So interesting thing is that if you study this solution, you find something very, very crazy and bizarre. But this solution has been verified, like things like sun, planetary motion, and there are observational proof that it is not the Newton's law, but rather the Schwarzschild metric, which described our planetary motion much, much better. What is the bizarre property this solution has? It turns out that if you have a very, very compact surface, okay, and if you study the space-time surrounding that object, you will see that very close to the surface, particularly at a particular radius given by this particular formula, 2gm by c square, where of course g is the Newton's constant, m is the mass of that object, and c is the speed of light. It turns out it creates a very special radius, which we'll call the event horizon. And the property of the radius is that you can only go inside the radius. You will never be able to come out. It's like a one-way membrane surface. And once you go inside, the force of gravity will be so strong that it will not allow you to come out. You don't have to worry about it, because if you study sun and if you calculate the Schwarzschild radius of sun, it will turn out to be 10 kilometers. Sun is millions of kilometers huge. So 10 kilometers is well within the sun, where Schwarzschild solution is no longer valid. So it means if somebody can take the entire sun and collapse it into a 10-kilometer ball, 10 kilometers will be what? Roughly half the Gandhinagar's radius, okay? So if you collapse the sun entirely into as small as Gandhinagar, okay, or maybe as small as 10 kilometers, I don't know, okay, then you will create a surface outside it such that you will never be able to go out of that surface, okay? Of course, this is completely, it's just mathematical fantasy. Okay, there is nobody is so powerful. There is no such system which can crush the entire sun into 10-kilometer radius. Okay, so therefore, this is just a mathematical fantasy. It's like in the mind of the mathematician. So there is this question. Everybody says, look, you don't need to worry about it, because this black hole is just an academic curiosity, and there is no such object in nature. So let's call this object, which is so small that there is a Schwarzschild radius surrounding it, and with a one-way membrane, a black hole. But then there is a Indian physicist, astrophysicist, Subramaniam Chandrasekhar, who studied the life cycle of stars in the cosmos. And he showed that no, wait, you are saying it's a mathematical subject, a curious object only, but it turns out there are massive stars, stars far more massive than our sun. And those stars can actually die. How do stars die? Stars convert hydrogen into helium through many other complicated processes. And part of that conversion, part of the mass is converted into energy by the Einstein's equations of E equal to mc square. But when they exhaust all their hydrogen, all their nuclear fuel, basically they have nothing to burn, nothing to create energy. As a result, the gravitational pull crushed the entire star onto itself. It's like a massive implosion. And Chandrasekhar showed mathematically, he proved that such an implosion will ultimately lead to objects very, very small called white dwarfs. If the star's mass is up to certain value, which we call the Chandrasekhar mass. But he showed that if the mass is more than Chandrasekhar mass, okay, then there is absolutely no way we can stop the collapse. And in fact, he conjectured that the collapse will continue forever and nothing will stop the collapse, and ultimately it will form a very, very compact object and lead to the formation of a black hole. I should comment here that I will also mention it in detail. In 1938, there was a student from Calcutta University, B. Dutt, who analyzed the same collapse problem in general relativity and came to a similar conclusion. And in fact, what we call today this conclusion as Dutt-Oppenheimer-Sider collapse, which shows on the basis of the Chandrasekhar's work that massive stars collapses and ultimately at the end of their life cycle forms a black hole. So with this proof, black holes are not just mathematical curiosity. There's a possibility that we have such object in nature in our universe. So therefore it becomes from mathematics to physics. So as I told you, the black hole solutions in general relativity are bizarre. They have this one-way membrane surface. But more than that, they have another very, very interesting property. And that property is at the center of the black hole, there is a space-time singularity. What does the space-time singularity? It seems that when you solve Einstein's equation and get the black hole solution, at the center, you get the density to be infinity. The mathematics suggest that, of course, nobody has gone to the center of the black hole, fortunately, okay, not yet. But the mathematics suggest that the whole mathematical structure of space-time itself become ill-defined at the center. And this is very, very bizarre. So more mathematically, people who want to understand what is actually happening, it turns out the whole structure of differential structure of the manifold of the space-time is ill-defined, and the wall lines of the particles cannot be extended further at the singularity. It's a very technical definition, but basically it means things are all infinite. And physicists don't like infinite things because we cannot do physics with infinite things. So existence of the singularity predict that the classical relativity theory by Einstein must be modified at the center of the black hole. It seems that the theory itself predict the theory will become meaningless at the center of the black hole. Of course, nowadays it widely believed the quantum theory will make the singularity vanish, but I don't want to go into that stage. So the whole idea is that the black hole solutions, whatever people have found by Schwarzschild and later by another solution by Raychaudhuri, which we call the rotating black hole solution, every such solution at the center of the black hole, it seems there is a mathematical singularity, but things are all infinite. Itself, the Einstein's theory is collapsing at the center. This is a bit bizarre. Not only that, not only for the black hole, we can apply general relativity for the entire universe. For example, you can make a model that you can think of the galaxies as like a non-interacting molecules or gas. Model the universe, entire universe is collecting of non-interacting particles. Each particle is a galaxy. Of course, you have to appreciate the imagination of the physicists. They can do this, okay, and still survive and get their salary. But believe me, this is actually quite respectable. Okay. So you assume that the universe looks same in all direction, okay, and there is no preferred point in universe. It's like a absolute Copernicus principle. There is no preferred point in the universe. Every point is same. Then, under these assumptions, you can actually solve Einstein's equation, and you can obtain the FRW metric exactly like how Schwarzschild solved Einstein's equation outside sun. Don't worry about the metric looks like, but it seems that for such space-time also, all of them suggest that the past of the universe at its millions, billions of years ago, the mathematics suggest that the entire universe started with a singularity. And again, at the singularity, everything is like infinite. Okay, all the physical quantities diverges. So both in the black hole solution and also in the description of the universe, it turns out the physics of general relativity suggests that there will be regions. I should be careful, singularity is not really a region, but it's okay. Okay, there will be regions for which the things will diverge and things will be extremely bad. Okay, and the theory itself predicts its own downfall. But note that so far we have found these singularities, these problematic things, is only for very special solutions. Okay, but existence of singularities are very, very dangerous because they are saying that Einstein's theory of gravity must be modified at the center of the black hole and at the beginning of the universe. It means that Einstein's theory cannot predict what happens at the beginning of the universe or what will happen if you fall into a black hole and go to its center. These questions cannot be answered by Einstein's relativity satisfactorily. You need new physics. But as I told you, these singularities are derived only in the context of very, very special theories, special solutions, like spherical symmetry, like universe which looks everywhere same and every point same. So the question is, suppose such conditions you relax, whether the singularities will exist or not. So mathematically, you are asking, how generic are these singularities? Are they independent of the assumption of symmetry, or they are dependent on the assumption of symmetry? So basically what we want to understand mathematically the solution of the Einstein's equation and use tools to answer this question whether the solutions of Einstein's equation generically without the assumption of symmetry contains the singularity. Please appreciate this is one of the foundational questions in science. You are asking about the beginning of the universe and what will happen inside the extreme case objects like black holes. and you're asking whether your laws of physics, what you know, are sufficient to describe this event, or you need completely new laws. So this is the situation. This is the situation of physics up to 1950s, where, at least the gravitational physics, where Einstein's equation gave remarkable picture about the universe in terms of black holes, in terms of cosmological solutions, but at the same time hinted that something is not right. At the beginning of the universe, at the center of the black hole, the laws of physics seems to be, making no sense to the scientists. The mathematics simply does not work out. So it is like a state of confusion, physics was. And this is the beginning of the scientific life of Amal Kumar Raychaudhuri. So with this context, I will enter into Amal Kumar Raychaudhuri's life and his education. Before we do that, let me also tell you the status of general relativity research at that time in India. So, in fact, the Einstein's paper, which were written in German, they were translated in English first time all over the world by two very eminent Indian physicists. This is actually not widely known. So please understand, in 1916, there is these two guys living in India at that time, colonial time, translated Einstein's paper into Germany by learning German and then by understanding the Einstein's mathematics. And these two people were M.N. Saha and S.N. Bose. And these two people will come back to my talk. So please understand, it means that M.N. Saha and S.N. Bose were both interested in the theory of gravity. Okay. And it will be, later we'll say it's a little paradoxical. Okay. And this is the first page of this translation. Okay. This is first time in the world. Okay, this is the first
dimension.
Great. Not only that, in 1930s, 40s, there was already a relativity research group in Calcutta University led by a famous mathematician called Professor N.R. Sen. This is the picture of Professor N.R. Sen. And the main emphasis of this N.R. Sen group was mathematical aspect of general relativity, compact star, cosmology. They were already started working on these things. And the B. paper on gravitational collapse came from this group. And unfortunately, B. died just few years after publishing this paper, and a great career is lost. At the same time, at the BHU, there's another very famous gravitational group led by a very famous mathematician, V.V. Narlikar, and his group was also interested in mathematical structure of relativity theory. So you see that even in that time, there was people, very, very competent mathematicians, interested in the theory of relativity. Okay. So this is the paper by B. Dutt, which was published in Germany, and it's on the gravitational collapse. Okay. So this is the scientific atmosphere in Calcutta, where there is some discussion of the theory of relativity. People are trying to understand what is this theory is about, trying to solve equations, and try to make sense of the situation. In this situation, Amal Kumar Raychaudhuri, who was born in Barishal, which is now in Bangladesh, in 1923, then he migrated to Calcutta. In his interview, he says his father was a mathematics teacher who always inspired him to give challenging problem in mathematics. Okay. He was a brilliant student. He's completed his BSc from Presidency College, Calcutta. The building you can see, this is the famous building in Presidency College. And then completed his MSc from the Science College, Kolkata. And this is the Taraknath Palit building of the Science College, which is also a very famous place for Indian science. And 1945 to 1949, AKR joined as a research assistant, kind of a PhD student, a little bit higher PhD student at the Indian Association for the Cultivation of Science in Jadavpur, Kolkata. So this is quite interesting. Okay. The thrust area of cultivation science at that time was mostly experimental physics and X-ray physics. They were trying to calibrate, understand the properties of material. They're doing very great thing. And Professor M.N. Shah, Meghnad Shah, was the director at that time. And he wanted to institute, and particularly the institute students and researchers, to work on the thrust area. Now, this is something which is quite unfortunate. It is like my director asking me to work on his field rather than my own interest. Okay, this is not the way research works. And Amal Kumar Raychaudhuri was almost forced to work on ongoing experimental works. But there's also some positive thing in working in ISCS, because ISCS library was a great library. I have seen library even today. It is one of the beautiful library. It's really great collection. At the Cultivation of Science Library, Amal Kumar Raychaudhuri self-taught himself into the various aspects of mathematical physics and theory of relativity. And he was also visiting NRSEN, going to their lectures, interacting with them, what they are doing, and he's learning the theory of relativity. And he is clearly understanding that his inclination of research is towards understanding this mathematical subject, which is new subject. Okay, like even in the West, very few people are really interested at that time. Slowly, the interest is moving on, and there are interesting new ideas are coming, and he wants to do research on that. Okay. He was writing papers. So this is a paper, very first few papers which AKR wrote. Okay, it's in Physical Review, and this is a paper. If you look at this abstract, it says the consequence of the perturbation in the expanding universe is investigated. Believe me, physics, I understand as a professional physicist, this is extremely new topic at that time. Even today, understanding the perturbations of the expanding universe is a quite interesting topic. So that means AKR, even at that time, working on fields, new field, trying to understand such mathematics and almost self-learning himself. Okay. So in 1949, he got a temporary position as a lecturer of physics at Ashutosh College, but he came back to cultivation and he got a kind of a semi-permanent position as a research officer. But the problem is when he wanted to get this position, so this is actually really the unfortunate part of our scientific culture, that the scientific establishment at that time could not able to understand the importance of the work. So for them, he is mostly doing things which, why he is working on things which nobody understands. So he is ready to work on cutting edge problem in general relativity, but the situation was complicated. Cultivation of Science authorities at that time gave no attention to his work in GR. They forced him to work on topics related to experimental studies. In fact, his relationship with the director, M.N. Saha, to be put very mildly, it is strained. Okay. It is said that there was a meeting between AKR and Saha, and AKR tried to explain what he's doing to M.N. Saha, but it did not help. And it cannot help because at that time, AKR is trying to solve and understand the new physics. So it's like a new person, is a young guy. It's very difficult for relatively older people to understand and appreciate the new physics. And it happens over years everywhere, all over the world. Okay. But in India at that time, the scope was very few. And if you don't have the patronage of the establishment, you really, cannot stand. Well, in the world, particularly the Western world, it was actually a great time. Slowly, a great time is coming. The golden age of relativity research is coming. And there are people all over the world, like John Wheeler in USA, Jeldovich in Soviet Union at that time, Roger Penrose in UK. They're working on new things, coming up, new mathematical techniques. Okay. And AKR is knowing about all those things. It's trying to work on those things alone, but zero help from the establishment and rather discouragement. Okay. And in India, the emphasis at that time was to follow the old style. Like S.N. Bose was there, very, very influential figure, but he almost stopped working on research problem. He was interested in so-called unified field theories, what Einstein was doing at that time. These are the theories which Einstein trying to solve in 30, 40 years after his publication of relativity research. Professional physicists, young physicists at that time, in physics, in science, there is no prophet. Okay. Einstein was one of the greatest physicists of all time. But once he gave general relativity, his theories were taken by the young people and modified into much greater complexity. Sometimes beyond what Einstein can even understand. Okay. And this has happened in the history of science always. But in India, the establishment few people in India, they wanted to follow the Einstein instead of the young guys. Okay. Emensa also never appreciated the importance of this. As a result, AKR walked without any appreciation and support. In some situations, he was even stopped to work on the relativity theory. But sometimes under this conditions, sometimes the best of human person comes out. And in 1953, he communicated his work on the singularity problem. And this is his famous paper. This is the paper which completely changed our view about the universe and cosmos. And in this paper, this box, the equation 11, is the first appearance of the famous Raychaudhuri equation. It is written in a notation which we don't use nowadays. We use modern notation, but this is first time. This is, I mean, to a student of physics and working in this field, it is actually remarkable looking at this equation. It's a very simple mathematical symbols. Okay? It ultimately tells us the fate of the universe and what happens at the inside of the black hole. That is the power of this equation. So let me explain a little bit why Raychaudhuri equation is so important and why we consider it to be at such a usefulness. Okay. So consider the laws of Newton's law of motion. What it says that if there is no force, things will move on a straight line, uniform velocity. Okay. What is a straight line? The shortest distance between 2 points. If there are 2 points, the shortest distance is the straight line. But it turns out, since gravity curves the spacetime, in the presence of gravity, you have to be very, very careful in defining the shortest distance between 2 points. And an example of this would be to think of a surface of a sphere. The shortest distance between 2 points on the surface of a sphere, if you are not allowed to go inside, okay, if you only live on the surface of a sphere, is of course not the straight line. It is rather the great circle, part of the ground of the great circle, which we'll call the geodesic. So in curved space, the straight lines are not really the straight line. They are rather the new curve, which we call the geodesic. In gravitational field, in the presence of gravity, particles move on geodesic. So the analog of force-free motion, see, gravity is not a force. So even the curved spacetime, there is no force acting on the particle. So instead of following the straight line of the flat spacetime, the poor particle is just following the geodesic of the curved spacetime, which is the analog of the force-free motion. So you can think of two geodesics on this circle, and you can see that the geodesics first diverge. Their maximum distance on the equator, and then they converge, and then they meet on the North Pole. One geodesic, so these are the great circles, start with the South Pole, distance between them increases maximum, and then they decreases and converge to the North Pole. So understanding the congruence of this geodesic can give us information about the nature of space. For example, by looking at this geodesic great circle, I know that these are lines on a circle. So this is 2 dimension. Although in Einstein theory, the curvature is in the 4th dimension, 3 spatial dimension and 1 time dimension. So you can think of a set of geodesic moving in space-time. Okay. So think of this room. This is a 3-dimensional space, and it is moving in time. We are all moving in time. So that constitutes a 4-dimensional block. So if you think time to be given vertically, so general relativists has this almost a crazy notation. They plot time in vertical direction. Let them do it. In that case, every slice, every constant time surface is a 3-dimensional volume. It's like this room. Look at this room or your room. Close your eyes. Think of every instant of time. It's a successive copies of this room at 430, 431, 432. Okay. These are all volumes at different times. And this quote unquote area of this constant time surface can change. Okay. Of course, I am saying it area, technically it's actually a volume. Okay. You can call it expansion. For example, you can start with this, it can expand. Okay, in time. Not only that, the expansion will call it theta. Theta basically says it's a mathematical quantity. It simply says the change of expansion per unit time. Not only that, the shape of the constant time surfaces can change. We call it shear. So for example, you can start with a circular room and you can end up with an elliptical room in time. Remember, this vertical direction is time change. There could be a rotation. I can start with a circular room, but I can rotate. Okay. So all these effects can happen when surfaces move in time. What Raychaudhuri equation gave, it's a mathematical equation. It gave us the change of the area due to these effects like shear, the change of shape, expansion, the change of area, code volume, and the also rotation as well as the space-time curvature. So this is the equation. The first term after the equality represent the change due to expansion. The next term represent the change due to shear. Next term is rotation, and the last term is the effect of the space-time curvature. So Raychaudhuri equation tells us that how things evolve in time due to the presence of the curved space. Okay. And therefore, by studying Raychaudhuri equation, you will be able to understand the consequence of the curvature of space-time, whether the congruents are converging or diverging or converging. In fact, Raychaudhuri equations with Einstein's equation together, you can show that in gravity, as long as the particles, everything has a positive energy, particles will always come close to each other. What it means is that just like Newton's theory, relativistic gravity is also active. Okay. This is, remember the first statement I made that there is no negative mass. Everything is attractive in gravity. Okay. This is the relativistic version of that statement. Okay. It's the Raychaudhuri equation. But the importance of Raychaudhuri equation is tremendous because it immediately gave us a mathematical tool to understand space-time singularity. Remember, we defined singularity as if I'm going into the black hole and then at the center, I'm not able to go further. So I can think of a stream of particles going into the black hole, and I can understand their evolution by using Raychaudhuri equation. And therefore, Raychaudhuri equation gave us a mathematical tool to understand what will happen to this particle. In fact, even in the original paper of 1953, AKR shows that if there is no rotation, the energy must diverge in the past of the universe, indicating the presence of the singularity. That proof was relatively simpler, but it is probably the first singularity theorem. But actually, the equation is far more powerful than even what is anticipated by AKR himself. Okay? Immediately, two great physicists at UK, Roger Penrose and Stephen Hawking, at first Penrose and then Hawking, understood the importance of the Raychaudhuri equation. And they used revolutionary mathematical treatment along with the Raychaudhuri equation to prove remarkable theorem asserting the unavoidability of the formation of singularity. They proved that these singularities which you see, they're unavoidable. Even if you change the solution little bit, you can add, instead of spherical star, you can have elliptical object. Okay, singularities will always form. And the crucial to their calculation is this Raychaudhuri equation. It is the mathematical tool, the first time, the screwdriver by which you unlock the mysteries of the singularities. And if you're interested, there's a popular science, semi-popular, I would call it fully popular. Okay. It may not be that popular. Article I wrote for Physics News this year after the Nobel Prize by Roger Penrose, which talks about an accessible account of the singularity theorems. These are mathematically quite complicated results. Okay. So this singularity theorem asserts the singularities must occur if following some mathematical condition hold. Don't worry about this mathematical condition, but these are the greatest result, one of the greatest results in mathematical physics. What they are saying is that coupled with Einstein's equation and the Raychaudhuri equation, they show that Einstein's theory of gravity, which we consider to be one of the greatest intellectual achievement of humankind, okay, cannot be the ultimate theory of nature. The predictability of physics demand that there will be a correction to the general relativity. And we still don't know what kind of theory will replace general relativity. And this is the ongoing research, one of the thrust areas in current research, okay? And to find a new law of physics, which in fact we have given it a name without even finding that law. We call it quantum theory of gravity, which will get rid of the singularities. But again, in all these theorems, the equation, the simple equation of Raychaudhuri is the crucial. This equation is undoubtedly one of the most significant scientific contributions from post-independence India. Of course, to list this contribution, one of which are the greatest contributions from post-independence India is debatable. I'm not qualified to do that because there are many, many topics. But almost everybody will agree that list is not very, big, at least in the post-independent India. But even an achievement of that level, okay, hardly anybody in India paid any attention to that. Raychaudhuri got a lecturer position at Presidency University. He didn't get a position even in Calcutta University. That is because his result was far ahead of his time. Scientific establishment never understood the importance of this result. And then, as always it happens, it is the Western recognition and praise for his papers from Hawking, Penrose, Stuttgart, all these great relativists, okay, ultimately encouraged him to submit his PhD thesis. Okay. So he submitted his PhD thesis, and his external referee was none other than John Wheeler, who is considered to be one of the greatest relativists of all time. And he made it sure that his thesis is accepted, okay, with due honor at the University of Calcutta, because that even was not very clear. Who will refer the thesis, okay, in India? Ultimately, AKR got a job as a professor of physics at Presidency College, and he served at Presidency College until his retirement in 1988. Raychaudhuri equation is not only for singularities, it is also a key input to understand the theory of black holes. This is this famous paper by Hawking, and this paper puts an extraordinary result that the area of a black hole cannot decrease. Basically, it means if you have two black holes, M1 and M2, collapse into a second black hole, it radiates energy, but its area always increases. And this gets to, I mean, there are remarkable consequences of this. You can show that the black holes are like thermodynamic objects. They have energy, they have entropy, they have temperature coming out from this results, okay? And this area theorem is a direct consequence of the Raychaudhuri equation. I mean, it almost comes from Raychaudhuri equation by few steps, okay? And it's no longer a fantasy, it's no longer a mathematical fantasy. Area law has been tested in observation as recently as the 1st July 2021. This is the paper using the gravitational wave observations and the LIGO result. People have actually tested area law, and turns out to be it is indeed true for that system they are considering. And basically, this is nothing but a positive test for the Raychaudhuri's equation. Okay. So this is no longer just theory; it is there in our world. Every day, black holes are collapsing, and that exactly following the law of Raychaudhuri. So it's not only this particular paper. Even after this paper, Raychaudhuri continued his work, and he has written many, many important papers on cosmological solutions of Einstein's theory. In 1998, he has written this another very, very interesting paper, which ignited a lot of debate and discussion in the community. Okay, it's in Physical Review Letter. It's called Theorem for Non-Rotating Singularity Free Universe. Again, you see that he's attempting to find a solution of general relativity, okay, in some way when there is no singularity. Okay. So these are remarkable mathematical. Apart from as a great physicist, okay, of course, he's one of the contributions in the world taken as a very high esteem. He was also an inspiring teacher. And at Presidency College, AKR created a remarkable academic atmosphere, igniting the passion of science among brilliant students. His lectures were legendary, and they were attended by students from other universities and colleges. This is this classical mechanics course book, which we follow even today and teach our students from these notes. He inspired a generations of students, and many of them has become very famous physicists later. Apart from that, if you talk to his students, and you will learn that I mean, he was a man of great principle and great honor. It's not easy to find such people nowadays, and there are many anecdotes and stories about him. If I can share one, for example, when he was about to retire, and Presidency College wanted to extend his, his service for another 2 years for this extension, he was supposed to get a signature from the doctor saying that he is on sound mental health. He refused it. And he said that, look, no medical practitioner can ever certify the mental fitness of a theoretical physicist. Okay, you should be judged, I should be judged by my work and my lectures. What you need that? And it seems that that created a lot of problem for the authorities. And he was always stick to his principles. And there are many, many stories like him. I mean, it's there. If you talk to college students, you will see his lectures, his stories are, I mean, when we were students, we used to learn this from his own students. Okay, they were already senior to us. The story of AKR is in some sense is the story of post-independence Indian science. He is a lone person working against all odds and achieving such remarkable results. He worked almost alone, without any help from the science establishment. All his recognition came much later, when only big name in the West like Hawking, Penrose, okay, Jorgen Ehlers, and particularly in India by the efforts of J.V. Narlikar, okay, when they started talking about him, that look, who is this man who created the Raychaudhuri equation, which is so important. We are getting all this remarkable result from his papers, okay, and only then we recognized him. So sometimes we were asked that why there is hardly any significant scientific breakthrough, at least in basic sciences, okay, from post-independent. Even in theoretical sciences, see, we understand experimentalists, it's not easy to have a breakthrough without large investment in technology. Okay, we were lacking technology when we started. Maybe today we are catching up, but without a huge investment, we cannot build a large hadron collider in India. But still, in basic sciences, where you need theoretical sciences, where you don't need such kind of investment, why there is not much significant breakthrough like S.N. Bose, M.N. Saha, or Jagdish Chandra Bose, C.V. Raman. There are only very few, like Ramachandran in Madras University, talking about. There are very few such breakthroughs. Okay, again, I'm not going to say how many breakthroughs are great, but the least is small. That everybody will agree. AKR's life story offers a plausible answer, in my opinion, at least. So the idea of scientist we have is this theoretical scientist like Einstein, working alone in the patent office, okay, writing down mathematical equation, and just by his genius, solving everything and coming out with great result, earth-shattering result. Okay, everybody is like amazed how brilliant that guy is. This story, like Madame Curie working in her lab, okay, alone with only a few guidance, okay, and coming up with the theory of radium or the theory of radioactivity. These were great stories, but believe me, post-World War II science is a different entity. There is not much of a chance of a lone scientist working in her own place, at least for physics, chemistry, this is definitely true. With a pen of paper, but coming up with revolutionary theory. That era of this, Victorian way of looking at science is probably over. Modern science is actually a team effort. Even if it is pure theory, it is a team effort. It required deep academic collaboration, atmosphere, interaction, free exchange of ideas, and support from the scientific establishment. Without that, you cannot, really give. The AKR, in some sense, is the best we can do. The scientific establishment in India during AKR's time did not follow the West. I don't think so. They are just following the West. They followed the old guards in the leading Western universities, whereas ignoring all the new development, which AKR was following. AKR was following all the new development, but they didn't. So it's almost cliche to quote Tagore nowadays, but I must quote this, where the mind is without fear, this famous poem from Gitanjali. A breakthrough in basic science is impossible without freedom of thought. You cannot, force people to work on topics which they don't want to do. A knowledge society cannot exist without scientific temper. In my opinion, the life of Amal Kumar Raychaudhuri is a story of a remarkable but unfulfilled potential. Would have been possible that if they has given proper help, if there was a environment surrounding it with mathematicians and others, like Hawking had Penrose, okay, such discussions was possible. Then he could have, you don't know, maybe the singularity theorems were developed in Calcutta or Madras or some places in India. So we missed that opportunity, okay, that to really unlock going ahead with the Raychaudhuri equation. So I would like to end here with this note, but before I end, I will show you a video of AKR. So this is from one of his interviews, which taken by his students. I'll show the citation. In this video, AKR was asked that what motivates him, all odds, what motivates him to go ahead into doing this great science. And then he read the dedication page of his PhD thesis, okay, in 1950s. So listen to what he says.
For the works that are presented here, the author is solely responsible. There having been hardly any consultations with others. However, in a wider sense, he feels indebted to many who in different ways have fostered in him the spirit of inquiry and given him sustenance and hope, without which no work is possible. And lastly, he feels glad that the universe, whether evolutionary or stationary, nevertheless exists and thus makes possible the author's dabblings and delvings. So I'm glad that I can make his dabblings and delvings.
Thank you. And these are the citations. I'm very thankful to Professor Sudipta Sengupta, professor at Cultivation of Science, for sharing his interactions with AKR. And if you want more information about AKR, you can check the documentary on AKR by Ayuka, which is available freely on YouTube. And there are these papers by Sudipta Sengupta, Shankar, also Jorgen Ehlers, and also Professor Naresh Dadich from Ayuka. And these are the good references to know about AKR. Thank you. Thanks.
Thanks a lot, Sudipto. It was fascinating, and I'm sure all of us learned a lot, because he's certainly one of the least known great names of Indian science. At least we've heard of some of the others, but I'm sure this is a revelation for many here. I think it's time to thank very warmly our two speakers of the day, Mrs. Tara Gandhi and Sudipto, for their wonderful talks on two very, very different figures of Indian science, and yet somewhere we can feel certain common threads, and their initial loneliness at least, but their great persistence, and how much we owe to them in very different fields, of course. So I think this was a wonderful session, and we look forward to more editions, 1 or 2 each semester of this series, and we'll continue trying to highlight lesser known figures of recent Indian science. Thank you everyone for joining us, and have a good evening.
Thanks.